I wanted to start with this picture. This is something I have in mind when I think about the security of my application. So it's it's a layer. You have different layers, and essentially each layer that is on top of the other relies on the security assumption of the previous one. So at the core of the security of the IC, that's something Jordan was talking about, which is essentially we are looking for increasing security. And one good way to increase security is to use cryptographic protocols, but secure one. And there are mathematical proofs that some of the protocols used on the IC are secure, but it's something that is kind of out of our control, at least out of my control. So always keep in mind that we are basing our security research and assumption on the fact that the IC is secure. I believe the IC is somewhat secure because there have been 2 years of production application. We haven't heard about any major hack. We've heard about a few security incidents, and I think Dfinity is very transparent on that, which is really cool. Whenever there is a security incident, they post about it, they explain what happened and how they solved it. There are a few examples on the Dfinity forum that you can check. And yeah, the code is open source. And the only thing I think is right now, maybe the incentives to hack the protocol are not so high. So I think as we'll go with the months and the years, the IC will become more and more secure as more value is stored on it. And yeah, hopefully we'll achieve a lot of security. So yeah, first layer cryptography, second layer of nodes. So we are also basing our assumption on the fact that you have nodes and those machines could be hijacked, but we are preventing that with the consensus. So as long as 2/3 of the nodes are honest, the assumptions of the IC are correct. So there could be a few malicious nodes, but still, yeah, we still have to think about those nodes and make sure that they are running somewhere safe and secure. Third layer is the layer of the protocol. So it's, I would say, a bit different from cryptography. And I think in cryptography, I should have included more like theory of the protocol, so how it has been designed. And then what I mean here is the actual implementation. So there might be, like, in theory, the cryptographic protocol or threshold protocol, for example, is secure and has been proved as secure. But it might be that the implementation contains some errors. And so that's also something that is out of my control and probably your control as well. The code is on Dfinity GitHub, and they have put a lot of effort into making everything secure. But once again, it's new software, and so there could be some errors. And the last layer, which is the one that is the most important for us and the one we'll talk about today, is the layer of the application. Jordan also mentioned before, just a few minutes before I was talking with him about the tooling. So there are a lot of toolings around, like the FX, for example, and that could be also some part of your development process that could have some security issues. But at the top, yeah, there is the application and how it's being used. So essentially how you code your canister. And let's see how we can make everything more secure. So before going into the code, I want to talk about something that is often forgotten, I think, is all as a user, how you can make sure that an application you're using is secure. Actually, I've discussed with a lot of people on the IT community, and this is a question that comes very often. People can be scared to put their assets into an application, especially for DeFi application. And that's very understandable. And the IC is a bit different in that regard to the blockchains that are out there. So the fact that someone can control a canister and upgrade it is a major, I think, security issue for, I would say, uninformed people. So if there is an application out there and they claim to do something with your asset and you have to transfer your funds, and the application is still being controlled by one developer or several developers, you are essentially trusting them 100% to not upgrade the canister and just take all the funds. So one way to mitigate that is to have a DAO or a DAO that controls the canisters. So that's essentially what's happening with OpenChat, Dragons. No, Dragons is a bad example. OpenChat, what was the other? Autonaut, all the applications that are going through SNS at the moment, so Mud Club and so on. If you have a DAO that controls the application, you're still subject to some risk because the DAO could upgrade and be malicious. There is no guarantee that the DAO will be always trustworthy, but it's still way better than having just one key person. And the most secure canisters are the ones that are black-holed. So I've already talked about that. You can remove essentially all the controllers, and so no one would ever be able to upgrade this canister. Then you also need to make sure that the code, you know what is the code running on this canister. So for that, you can check the WebAssembly module. If you go on the dashboard, you can check the module of the WebAssembly installed in the canister. And you should be able to compare that with the code that is out there. So essentially, let's say on GitHub, you should be able to take the code on GitHub, compile it, following the tooling that the developer have used. And at the end of your build process, you should have the same WASM hash as the one that is on the mainnet. If that's not the case, you don't have a way to be certain that the code that is running is actually the code that the developers claim to have written. So they could have introduced a backdoor or any kind of issue. And the one other important part is maybe the code is the good one and it's a DAO and so on, but doesn't mean that there is no security issue in the code. There could be a lot of security issues. And so if the code has been audited, that's probably one good way to know that there are less problems. So audit is not it's not bulletproof. There are actually different ways to audit. There are different, I would say, security guarantees that some type of audits. For example, there is something called formal verification. We can talk about that later, which is very, very, very gives you very, very huge guarantees that something is correct. And then there is the, I would say, traditional audit, which is essentially a developer that is very, very that has been very, very, very educated on security, that will take a look at the code line by line, like do some tests. And this is already a first layer of security, but it's not bulletproof again. Last part, it could also be that the application is correct, like everything is working perfectly, but still your data, so you wouldn't notice, but your data that you're using on the service is completely being leaked. So that's something that you probably want to avoid as well. And so we will talk about that later, especially regarding the nodes. Okay, so that was as a user. Now, as a developer, there are way more things to take into account. I've listed some of those attacks or problems that you could encounter, and then Jordan will go into specific examples. The first one that I've found is something called cycle drain. Actually, the issue is that someone could call your canisters, some of the methods, until the canister is out of cycle. So it's possible that you have some methods that are very, very, I would say, computational expensive. And so if you don't implement any kind of protection or any kind of rate limiting, so limiting the number of requests, it's possible that someone could call your canister, just DDoS the canister, and essentially, keep draining your cycles until the cycles reach 0. In this case, when the cycle of your canister is at 0, well, actually, sorry. When a canister is being drained, the cycle will hit something called the cycle threshold, the freezing threshold. And so the freezing threshold is something that you can set. By default, it's 1 month. And it's a duration of time that you have to give more cycles to your canister before the canister is being deleted automatically by the system. So yeah, one thing could be, I don't know, you go into vacations, you forget about your project, and someone just drain all your cycles, and you come back 2 months later, and your canister is gone. So that's a huge risk. You lose all the memory, you lose all the memory of the canister essentially. Another type of attack is memory attack. So if you have a method where users can write into your memory, and they can write a lot, they could abuse that again, and they could write and put a lot of bytes and information into your canister until you reach the limit of the canister. So that's also something you have to take into account. If you reach the heap, as we said before in a previous lecture, you will encounter a lot of strange and a lot of issues. So you want to avoid that. And so you shouldn't probably let anonymous users or any kind of users write too much into memory. Though, there are some. It's not as bad as it sounds because there are already some protections that you could put in place. I'll skip intercanister code for now because I'll talk about that at the end. There is also authentication. So what I mean by that is just preventing some people to call certain functions. It's very easy to do. As you saw previously, we can check the color of any method on a canister. So for example, you could block all your methods so that an anonymous user couldn't call those methods. That would be already a first protection layer for like memory attack or cycle drains, because users would have to create an identity, which is already like quite expensive economically. So that would already prevent some kind of attack, or at least reduce the risk. So yeah, just like implementing authentication checks. That's what I meant by authentication. The fourth one is economic attack. So this one, especially for DAOs, is pretty important. If we put the control of the canisters into the end of the DAO, it's possible that someone could buy all the token, and depending on how the voting power is structured, this person could take over. And so this person could, essentially that's a risk. They could upgrade the canister, do whatever they want. And actually, we've already seen that happening on the IC. There was a project called SNS1, which is essentially a kind of empty SNS. It was a test, the first one that was officially launched. So there was no project attached to it. It was just to test the SNS framework. It was launched, and it was up to the community to essentially do something with it. That's what Definity said. And what happened is that someone, so the Dragons project, they've bought all the token, and so now they can essentially pass any proposal they want. There is one person which has so many tokens that they can do whatever they want. It was not too much of a problem because it was a test SNS, so it was okay in this case. But that's something that could happen in theory to any DAO that is on the IC. It's something that is taken very seriously. There are ways to make that less likely, but that's still one vector of attack. And I would say it's one that is quite specific to DAOs, so that's interesting. The last one are the upgrades. There has been a lot of issues with upgrades and people that lost their canister like this. So you remember those pre-upgrade and post-upgrade methods? So Jordan recommended to use stable memory and stable bitrate. It's a very good recommendation because you don't want to mess too much with those methods. One thing that could happen is that you essentially trap during the pre-upgrade. And so if you do that, you essentially, your canister is bricked. So like you can never upgrade it anymore. That happened to some canisters, and it's not something you want. Generally upgrades are kind of risky moments during the life of a canister, but even more risky when you have to serialize, deserialize. So that's why we recommend to use stable memory as much as possible. Okay, and last one is intercanister call. So from my experience, that's where all the mistakes, like 99% of the, maybe 90% of the problems and hacks on the IC so far have come from. So there is the way to do inter-canister call with the actor model, essentially a sync await. So you send a request and then you receive an answer later at some point. And the problem with that is the mental model for it. So you essentially have to put yourself in the canister position, and the canister can be called from anywhere at any point. And so, for example, let's say you have a function which, I don't know, do something, and you assume the state to be somewhat stable, like not moving. You do an inter-canister call, and while you're doing it, there is another request coming that modifies the state. And when it comes back, it's not how you think it is. I hope we can come up with a good example. I don't have one right now, but yeah, that's essentially the main problem. Also, inter-canister calls. If you're calling malicious canisters, you don't really know what they're going to answer or if they're going to answer, and that could be one big problem. So yeah, that's about it for the overview of it. Let's go into the examples. No. I think you're muted, Jordan.
Hello.
Yeah.
Okay, so yeah, as Seb is going through this, there is so much to talk about when we discuss security. It's going to absolutely be impossible for us to discuss everything. And I highly recommend digging in and studying yourselves if you're ever going to try to take this seriously, right? So let me give my own overview, like Seb said, and then I'll get into some specific examples on the maybe the most important, obvious topics. So first off, Seb talked about crypto and the nodes and the protocol and all that stuff. You're depending on the security of everything that your application is built on, and then you are basically responsible for the application logic itself. So, because you guys are all building with Azel, I just want to point out again the disclaimer of Azel. That's going to be the first thought that you have if you are, auditing an Azel canister, is that there are going to be unknown security vulnerabilities in Azel itself due to the fact that it's so new. We don't have reviews or audits yet, and the core engine we're using is currently experimental, much more so than the engine we'll be switching to. So that's like the base layer that you think of. Then I highly, highly recommend going into this official documentation here at internetcomputer.org, security best practices. They talk just in general about security, and then they focus on canister development and web development. And there's just tons and tons and tons of information in here. Like general's not that big, but look how huge canister development section is. I guess it's not that huge, but there's a lot of good information. Also, there's this really cool blog post called How to Audit an Internet Computer Canister. And we'll be probably focusing on this coding stuff for today. And then I think Effective Rust Canisters has some information in it as well, which I believe the security best practices document pulls from. That's what they talked about here. So let's get into some actual examples. So like Seb said, inter-canister calls possibly is the most error-prone area in this whole thing. So let's go talk a little bit about inter-canister calls and what's actually happening under the hood so that you understand what's going on here. So let's just start with the normal update call. Okay, and we'll make some global state up here, just a string. Let's see, global state, yeah. I'll just show you some issues that happen here. Okay, so first thing to understand is the nature of persistence with your state. So let's say we pass in some message here, and then we want to store that in the global state. Remember, this global state is representing, stable structures, some data, like any kind of structure or data that you're storing that you have available persistently, right? So,
Jordan, can you
yes.
zoom in a
Oh
bit?
yeah, sorry. Let me get my terminal zoomed as well. Okay. And we don't need that to return. Actually, I will do it. Okay. And then let's just make another query method real quick so we can read that state at any time. Okay, so if we execute this, it'll just work as you expect. Every update call where we pass a message in, this will be updated and we should be able to read that. But my question would be, what happens if you throw here? Or if you trap? So you could either throwing will result in a trap, or you could just explicitly call the trap function as well. These are equivalent. So I'll just leave that. Oh, what happens here? Well, let me show you. But basically what's going to happen is you will set the state, will throw. The throw under the hood will result in a trap, and all state changes in this message, and there's only one message here. This is just every update call is at least one message, right? Everything that happened in this message will be overturned, or what's the word? Undone, wiped. What is the? I guess rolled back. Yeah, the state changes will be wiped. They'll be rolled back. So let's call this if x can't call async await. Global state problems. Should say message 0. Okay, so we threw the error. So if we call read global state, so this happened, and then it threw. If we call read global state, this should be empty because the state change will have been thrown away. And it's empty. So that's good. We can open this. Okay, so that's what you would expect, right? Okay. What happens though if we do an asynchronous call? And this is the source of all these problems. Understand this concept, and I don't know, you'll just be in an absolutely amazing place. Okay, imagine right here if we do a cross canister call. What's the problem? Oh yeah, dot call. Okay, what would you expect to happen? I think naively thinking, you would think, oh, well, it will throw, which will trap, and all previous state changes will be undone. But that is not the case. Whenever you have an await point where you do some kind of asynchronous operation, you add another message, basically another update call. Everything before this point is one update call. It gets committed, and then everything after this point is another update call. So if we execute this, what's going to happen is we will save the state. We will do the async await. It will commit that state. Then in the response, it will create another message under the hood, throw, but there will be no state to undo because the state is already committed. So this is working just slightly differently than you might expect. So now if we call, I guess I can use, now if we call this message 0, okay, it did fail, But watch, see, message 0 is still there. That was not the case without the async await. Okay, that is the main concept. You must drill this into your mind. Every await point is going to create, it's going to commit state, and then a new update call will be created to handle that response. So this is a little scary because of all of the problems that can happen here. So if you're depending on global state, you need to understand that the global, sorry, that was one concept. Now let's go to a separate concept that might be related. This global state can be changed from under you during an await. So when we call global state problems and pass a message in, message 0, it's going to be message 0 at first. But once we hit this await, other update calls can run while our await is doing asynchronous stuff. So anybody else could decide to call this method and change the global state. So if we're trying to do something, if global state equals message 0, let's say there's some crazy password no one can guess, right? And I don't know, we'll print something like you can access the funds. And then let's say this asynchronous call is, you have to go do some asynchronous stuff to prepare to provide access to the funds. If you do this, this is extremely security prone, right? Or risk prone. Like anybody could come in during this await and could overwrite this. So let's show this working. Let's just make sure. I'm going to await a bunch of these so that it takes a long time. Okay, so that'll take a while. Okay, and I'm going to let's see. Let's deploy it. So I'm going to provide the password to this function. And remember, let's pretend that this function is like going to transfer some funds to somebody or something. And you can only do it with this password. And this is just representing some kind of authorization check. Okay. If I call it once, then we should be good. We should see printed over here, you can access the funds. Okay, but watch this. Watch this. If I do this and then change it and do another call, let's see, we might not be able to get it to work. Did they all return? Okay, look, it didn't work. And I could, if we do it again, it should print out that you could not access the funds. So do you see what happened? At least what I'm assuming happened here, right, is I did my first message and the password was correct. And I stored the password globally. Then I did a bunch of asynchronous stuff. And while this stuff was happening, another message came in and overwrote the password. So that when the first call to global state came back, it went and looked at the global state. It no longer had the original password from the message. It had something else. And therefore, I was not able to access the funds. So I could do it one more time. I'll call it like that, and then I'll call it like that a few times just in case. Okay, and when that original, yeah, see, look. Well, when did that come in? Oh, it just came in. You have to time it right. So I think it worked the first time, right? Call. Yeah, I only did 2 calls that time. And look, none of them could access the funds. So the point is, like, it's kind of like undefined. Like, you don't, like, sometimes it could work, sometimes it couldn't work. So you really, 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 really want to avoid this kind of stuff. Okay, so how would you avoid this? Well, basically, before you do an await, you need to store everything in a local variable. So, like, grab the password out right here. Don't do that. Or, if you need to store it globally, you can do that. But then right before you do an await, grab that local thing right there, and then you could put it right here. Okay, now it doesn't matter how many messages come, it will work every time. Because this local state is going to be saved across the waypoints. It's the global state that will not be saved. Any questions on this?
No questions so far.
Okay, now if I put in that message and then change it real quick, we should get 2 responses. First, I could access the funds. Second, I could not. And if I do it again, it should be the same. You can't access. Yep. So 1, 2, 1, 2. Every time I should be able to access the funds. Okay, so be just extremely careful when you're doing these types of things, right? Okay, so let's go over some other stuff. So inter-canister calls. We went over some of these things. Reading global state before issuing an inter-canister call and assuming it to still hold when the call comes back. That is something you should not assume. Possible common sources for bugs, that's what it's saying, right? Changing global state before issuing an inter-canister call. Changing it again in the response handler, but assuming nothing else changes the state in between. Again, I think it's basically the same thing, like just expecting your global variable to not change during your await. Changing global state before issuing an inter-canister call and not handling failures correctly, e.g. when the code handling the call back rolls back. Yeah, so I think we showed that earlier where if we throw right after, it's not going to undo state that happened before. So you might get into an inconsistent state. Okay, and then rollbacks. Basically, on the internet computer, there are 2 ways you can fail a message. One is by trapping, and one is by rejecting. And you have access to both of these through the IC object. So IC.trap will do just like what throw does, and execution, roll back all state in that message, and you can pass a message in here. But there's another thing you could do, which is reject, where you also pass in a message. Rejects current call with the private message. And apparently, reject does not roll back your state changes. It will, I believe, end execution, everything's done, show an error message, but it's not going to throw away your state. So you just need to be careful. Don't reject when you mean to trap, and don't trap when you mean to reject. In ASL, though, any throw or any uncaught error or anything, I believe, and I mean, this would be part of when we do our own security stuff, we would go and we'd be absolutely certain about this, but I believe everything ends up in a trap. We don't reject unless you explicitly reject. Also, guard functions reject. So if you do use a guard function, you should keep that in mind. And I don't think we've shown you guard functions, but they work like this. Oops. Result. It is. Result. guard result. Yeah. One. There we go. So a guard function, you can basically hook it up to your update or query methods, and you can say, basically, this function must return OK for it to work. Oh, and oh yeah, it's a little weird. Yeah, okay, that's a little weird. So okay, you don't have to do that if you don't want to. You can just do like, okay, no. That's another way to do it. In this case, though, if you say error, it passes in some kind of error, like something happened. I believe that under the hood, a guard will actually reject. It will not trap. So you need to be aware and careful of that. Okay. Then talking to malicious canisters, you just have to keep in mind that if you do a cross-canister call to a canister that is malicious, he goes into details here, like the canister might, I guess, try to DOS you. It might take a very, very long time for that call to return. And apparently, the other canister could give you invalidly encoded candid. I haven't checked yet, and we're re-architecting everything. So this is something we'll definitely keep in mind with the re-architecture. But if invalid candid comes back, I'm guessing that we would trap under the hood, but I'm not sure on that. So I'm not sure you can really handle this. This would be for us in the CDK. But you just have to keep in mind that these calls, I mean, I guess what he's saying is this await could, like, management canister you can trust pretty well, but let's say it's just some other person's random canister. Well, I mean, it just might take forever for this to ever return. Though he does say it's designed, the internet computer is designed to guarantee a response eventually. The other party can busy loop for as long as they're willing to pay before responding. Worse, there are ways to deadlock a canister. So I guess it is technically possible to get into, it sounds like it's possible to, sounds like it is possible to never get a response. So that is something you need to keep in mind. But also, it seems like the protocol itself needs to come up with some way to maybe time out or something so that we don't, as the callers, we don't get into these situations. Okay, now all this stuff about canister upgrades, pre-upgrade, post-upgrade. If you embrace stable structures, like Seb was saying, it's not necessarily an issue for you. But let's just talk about it real quick. So you have a pre-upgrade function here. Remember that this function runs when you try to upgrade. It will run before any of the code is changed and before any of the heap is wiped. If you trap in here for some reason, if there's an error thrown, or if you do itc.trap, or if there's some uncaught error, it's over. Your canister can no longer be upgraded. It will be just stuck the way it is. There's just, as far as I know, there's no way around this. It doesn't matter what language you're using. And it makes sense if you think about it. If this function runs before you upgrade your code and the function can't finish, then you can't, well, what would you do? Because you can't change this function. I mean, unless the trap is like non-deterministic somehow, right? But or based on randomness or something. But if the trap happens every time, then it's just over. So you need to be extremely careful with your pre-upgrade. Best thing to do is to not use a pre-upgrade and to just use stable structures or stable memory directly, and then you just don't have that problem. And he just talks about that here. The pre-upgrade is a major risk, and it's very scary. A lot of this is talking, though, about serialization and deserialization in the pre- and post-upgrade functions. and Motoko specific limitations that I'm not sure it has anymore, like the 2 GB limit basically, but Azel and Rust do not have this issue. Okay. I mean, this is all about upgrades. So, I mean, if you embrace stable memory, stable structures, I just think a lot of this just disappears because it's just in real time doing this stuff. And so upgrading is not that big a deal. Though you do need to be careful with your stable structures across upgrades. Well, if you change the structure of your data structure, like the types, you will need to figure out how to do that migration. So I guess you would need to be careful in that. And in that case, you might use pre or post upgrade to do migrations on those stable structures. So in that case, you could get into a problem. Prompt upgrades. Yeah, so here's a weird problem. Technically speaking, you should not just call upgrade on your canister if there are cross canister calls happening. Because let's say you initiate a cross canister call, like let's say this call goes out, and then you upgrade this canister, you change the wasm binary under the hood. Well, when the response comes back, it's going to try to call a callback method, which is going to be basically the rest of this function. But if you've changed your binary, changed the functions around, it can just call some random function. And in Kybra, building the Python CDK, we actually ran into this problem. And it was absolutely crazy because we had no idea what was happening. Our tests would just like randomly fail. And finally, one of Dfinity engineers, as we described the issues, somehow came up with, oh, like it's because you're swapping the binary out during a cross-canister call. So when it comes back, it's using like an index, a function index into the WASM binary, and that index doesn't exist anymore. It's just something else. So it was just doing a random behavior. So you need to stop your canister, which I guess will allow all outgoing requests to settle, I suppose. I mean, I assume that's what would happen. And then you can upgrade it, and then you can start it up again. Again, this is something that I feel like the protocol needs to handle so that when we upgrade, it can be just smooth. But as far as I know,
Yeah, actually, you cannot stop a canister if there are still outgoing requests. So that could be an issue. And I don't think there's a solution right now.
oh, you like if you try to stop, it will just not let you stop, or will it, as it's trying to stop, will it wait until those come back and then stop it for you?
I think it just refused to stop. It says that it just refused to stop. Pretty sure. Yeah.
Okay. Yeah, it's kind of messy, kind of a problem. Okay, backup and recovery. I mean, you just need to be careful with all these upgrade problems and cross-country calls and things like that. Mostly, I think this is about upgrading. If you lose all your data or you run out of cycles, then everything will be deleted basically. So I believe the Computer is working on, or Dfinity is working on some capabilities that will allow canisters to be backed up and stuff, but you might have to do off-chain backups depending on the nature of your application. Be careful with time. When you call time within the same block, it might return the same value. So apparently, even across upgrade functions, if they're under the hood in the same block, the same value will be returned. So don't expect time to be different every time you call it. Also, don't expect math.random or any kind of randomness to be different inside of a query function every time you call it. Let me just show you this. What will this be? Just a number. If you ever do anything random inside a query function, you need to think again. So let's deploy this. This will return the same number every single time because it's in a query function, and I'll explain why. Oopsie. Oh, shorthand notation unsupported here. Oh, I don't know why that is, but we don't need the guard function. kept focusing on this. Ooh, also I guess we're running out of time. So, I mean, there's more we could talk about here, and there's just a ton of topics we could cover here. So we probably don't have time, and we'll probably need to answer questions. So I'll just finish showing you this, and then we can answer questions. Okay, if I call randomness, check it out. See, it's the same number every single time. But if I put it in an update function, then it will be random every time. Why is that? Well, how at least Azel's working under the hood, and I guess I don't know, but it'd be interesting to know if Rust and Motoko have these same issues. But with the randomness under the hood, everything is seeded from the randomness of the internet computer, right? And so we have a random seed. And at least for the math.random implementation, it keeps some internal state to basically allow the seed. It keeps like an internal, I don't know, some kind of counter or index, so that from the same seed, you do get something random every time. But in a query function, that incrementing under the hood is not saved. So it generates randomness, tries to save the state of that, but then gets wiped. Whereas now that it's in an update function, now that it's in an update function, yeah, every time it's going to be different. Yep, because it's able to use the same seed, but keep some internal state that will effectively make it, I guess, pseudo-random to you. So those are just a few issues to look into as you're developing your canisters.
Yeah. Thank you. We have some questions. So some of them, yeah, there is a question. What about using promise.race to avoid the issue with I think it was with the Intel canister call.
Promise.race?
Yes, I'm not familiar with.
The promise.race static method, just reading the documentation, takes an iterable promise as input and returns a single promise. No, this return promise settles with the eventual state of the first promise it settles. No, I don't think that will help.
Yeah. Yeah. Also, it's a ICP issue.
It is the core protocol. It's how it works under the hood. And this is very similar to how like Node.js or other like single-threaded kind of event-driven systems work. Is you strictly order every operation or every function that's going to happen. You execute, you execute, you execute, and if an async operation happens, you spin that off. When it comes back, you basically put that message back on the queue, and then you just keep executing. And that's exactly what's happening on the computer. Executing all update methods. When there's something asynchronous, it goes and spins that off. And then when it comes back, it puts that response back in with the other update messages, and then just keeps executing all of them. So there's just no way to get around that.
Isn't just so all the issues we mentioned, I mean, that's what you just said, but isn't it just a multi-process / thread race condition? Sorry, I'm not explaining the question very well. The question is, isn't all of this just a canister version of multi-process / thread race condition?
So it's not. So they're not threads, and they're not. So it's not. It wouldn't be similar to threads because it'd be similar to. No, it's not. It's not multi-threaded. It's single-threaded. You have to keep that in mind. And it's not multi-process. I mean, technically, it might be more multi-process than it's multi-threaded, but there's one thread of execution ever of your, that has access to the mutable state of your canister. So that's what's happening. under the hood. So it is not, yeah, it's not multi-threaded. There's not, you don't have multiple threads that have access at the same time, but you do have concurrency. So there's no parallelism that has access to the shared mutable state, but you do have concurrent update calls that have access. So look into Node.js, how that works under the hood. Look into Nginx or something, how that looks under the hood. Any single-threaded event-driven system, this is what's happening, basically.
Mm,
Well,
how
async await
does
can be used for multi-threaded stuff, but in JavaScript, generally speaking, async await under the hood does single-threaded event-driven stuff.
do you know how OpenChat upgrade their canisters? Yeah, I actually do know a few things. So essentially they have a canister that is kind of managing the entire fleet of their of canisters that they have. So yeah, whenever they have a new user, they create a new canister, and essentially they keep track of the version of all those canisters, and they have the kind of their management canister, their own management canister that will trigger upgrades whenever they have a new version to all those canisters. And I know it takes a long time actually. Like they've run into issues because it would take several hours to upgrade all of their canisters. But essentially they just do it and they just keep track of what's happening. So they keep the version of each canister in a registry and they just do it. So they would have to wait that you're not using the application at the same time. Yeah. I don't know if you want to add a few more things, but that's
I don't
all.
know. I just know that their upgrade process, I think, is like very complicated. It takes a very long time.
Yeah. Mm, I don't see any more question. Yeah. Do you have some ideas of how you're going to audit the ASO?
Um, yeah, what we want to do is first we want to like automated property tests. Property tests are specific types of tests where you can generate tons and tons of random inputs to like test crazy things. So we're thinking of extensive property tests. Honestly, though, with our new re-architecture, we're thinking that the whole project is going to be way simpler than it has been. So we'll see how many of those tests we need, and then we'll probably do our own internal review where we'll just deep dive into our own security study and then just go through it, and then maybe uh, get some help from organizations either for free if possible, or maybe pay for an audit or review or something. And it's different than it's not like a smart contract audit, right? So
Yes.
I don't know.
Yeah, it's very different. But yeah, I wonder like who would be able to audit such a project. But yeah, it's gonna be very hard to find someone actually. Like I guess you need to know a lot about SDK and you need to know a lot about DIC and indeed Rust. So yeah,
Yeah, and we'll see.
not
Like maybe if we show people like, hey, we have all these tests, we're using this engine, we're using these Definity dependencies. Uh, Maybe altogether it's like, hey, like review it yourself. It's an open source project. I don't know. We'll see. We'll head towards what we call 1.0, and we'll probably enter like release. It'll just get more and more mature over time, basically. So
yeah, great. So that was the last lecture with you, I think. Tomorrow we have one, which is less technical. It's about finding a job in the ecosystem. But yeah, that was the last lecture with you, I think. So thank you, Jordan.
yeah,
And
thanks.
yeah, good job. Like I mean, I've seen the Hazel from the get-go, from the early days. And yeah, it's impressive. I'm going to write a little review after this bootcamp.
Sweet.
But yeah, great.
Okay, awesome. Thanks, guys. Thank you, everybody.
Thank you, everyone. See you in 3 hours for the mentorship session. Have a good night. Good day, good afternoon, end of the day. Bye.